Yes, so today's lecture is going to be about hidden Markov models. But before we start with this, we will, as usual, have a quick recap of last week. So last week we introduced some basic probability theory, basic axioms, the difference between conditional and joint probability, independence, and Bayes theorem. We were looking at a problem where we have a sequence of elements, and we were interested in predicting the next one based on the history, based on what we have seen so far, and for example, that would be words in sentence. So we have seen so many words this far, and we want to expect to predict the next one. But then it turned out that looking at the full history of the sequence, it would be difficult it's expensive to compute, and it's more importantly going to be very rare that we have actually seen all possible context or history. So we introduced this Markov assumption, which basically says that the whole history could be approximated in the last n-1 elements, and n-1 could be from 2 to 8 to 10, an arbitrary number, but not the full history. And based on this assumption, we could build something called the n-gram language models, which predict the nth word based in a sentence based or conditioned on the n-1 previous words. We used maximum likelihood estimation to compute or approximate again the conditional probabilities that we need for the n-gram model, meaning that we learn the parameters of the n-gram model using maximum likelihood estimations. It also turned out that if we have 0 probabilities, this will lead to cancelling out the probability of a full sequence. So if only one bigram doesn't occur in our corpus, this will get a 0 probability. So we had to introduce this concept or technique of smoothing, where we shifted the probability mass a little from the frequent events to the infrequent ones. So basically we were doing this part, right? So we were looking at the string and computing the probability of this string. This is a language model. In the end, it will compute the probability of a given string in a language. So that's done. Today, what we want to work with is sequence labeling. So we are given a sequence, and we want to predict a sequence of labels for this input sequence. So a typical example would be part of speech tagging. That's the main application that we will be working with. So given this sentence, flies like flowers. I think we had time flies like an arrow last time. We want to predict what's the part of speech tags, or most probable, most likely part of speech tags for this sentence. And since we will be saying this part of speech tag so many times, we will start with a short and brief introduction, linguistic introduction to what are part of speech tags. Probably all of you know it, but maybe don't know that it goes with this name. So part of speech tags, as I just said, it has so this concept has so many names. We can speak about part of speech tags, or abbreviated or the acronym POS, lexical categories, word classes, morphological classes. All of these refer to the same concept. So we talk about part of speech tagging or lexical categorization, for example. And traditionally, or actually very often, you will find part of speech tags defined in terms of the semantics, in terms of the meaning. So words that have some sort of semantic coherence among each other will be grouped into one class. So a typical example would be nouns, for example. Nouns is an example of part of speech tags. Defined in terms of semantics, this would be like saying nouns are naming words. So words that give names to entities, to people, to places, etc. But we also notice that these groups or these types of part of speech exhibit some syntactic and morphological features, or not features, but distributional properties, let's say. Meaning that nouns, for example, will occur nearby a determiner. So you will see a determiner, and then that would be followed by noun. Not necessarily all the time, but this is a property. This is a syntactic distributional property. So a morphological property would be that nouns could be inflected in the plural form. So you have phone, phones. So this is a feature of this group of words that is under the part of speech nouns. This definition, this syntax or morphological based definition, works for us more than the semantic one, because we were working with data-driven approaches, and we have data sources or data sets that encode the syntactic information together with the part of speech. We generally distinguish between two supertypes, maybe, of parts of speech. So there's an open class type of part of speech tags and a closed class. So in the open class, we are talking primarily about nouns, verbs, adjectives, adverbs. So this is a class of parts of speech that's called open because it's easy, or relatively easy, to add new words to these classes, to these word classes. Meaning, when there's a new concept, so say iPhone now it's a word in English. It didn't exist, maybe, I don't know how many years ago. Or a tweet, for example, it's a verb and it's a noun, and it's easily added to the lexicon. So you could easily add, update, so words that were used as adjectives become also nouns at some point. And you can also delete. Some words will disappear. So that's why it's called open. So there is you can't actually have a fixed set and say that this is all the possible nouns, because maybe after a month there will be new nouns. But closed set is in contrast to open class. Closed classes would be things like prepositions, like determiners, like pronouns, where first of all the size of the class is relatively small, and it has a relatively static membership, meaning that it has it's difficult to add a new preposition. We don't coin new prepositions every now and then, right? So it's very rare that we add to these classes. So these will have a fixed number of words or of members. And these types of words or that belong to the closed class are usually function words. Function words, like prepositions, like determiners, etc., which serve a function in the sentence more than it provide a meaning. So it helps us build a syntactic or a linguistic grammatical structure. So very quickly, so nouns generally described as words that describe objects. So Oslo, snow, people, etc. So this is how we generally would define nouns. We can subdivide the class of nouns into different types. So we have proper nouns and common nouns. Proper nouns are things that are naming entities, people, cities, etc. Common nouns is everything else, the rest. That is not proper noun. So we distinguish between countable and uncountable. So countable noun would be a noun that is modifiable by a numeral. So you say 2 books, 3 books, etc. That's countable. Mass nouns are those that can't be modified by a numeral, like water or information. So you can't say 2 informations, or that's not correct. And then we can also distinguish between plural and singular. These are not very important. So I mean, it's just for you to get the concept. That's not that's not central to the course really to understand all of this. Verbs, it's the set of words that describe actions compared to the set of words that describe objects, which is nouns. Again, verbs can be subdivided into transitive, intransitive, so verbs or transitive. So verbs that take an object, those that don't take, etc. And then we can also subdivide them in terms of tense, etc., etc. And adjectives are words that describe qualities or properties, and when they are normally modifying nouns. Again, they could be subdivided into groups. So we could have a part of speech tag saying that this is an adjective in the comparative form, like smaller, or we could also classify or define parts of speech tags depending on the position of the adjective. So a predicative adjective would be something like the cat is unhappy. An attributive adjective would be the unhappy cat. So it depends on the position of the adjective. Adverbs are words that are very similar in a sense to adjectives, but they modify verbs, and they also could modify other adverbs or other adjectives. So this is just an overall view of what kind of part of speech tags to expect, so that you're not completely lost when you look at the output of your program, and the assignment, or when we look at the examples now. Oh, there's more. Yeah, closed class words. So again, these, as I just mentioned before, very quickly, these are types of or parts of speech tags that are specifying closed word classes, things like prepositions, determiners, pronouns, conjunctions, etc. And these types of words, they don't provide meaning. They don't have much meaning to themselves, but they help us either further specify the things that we are describing. Like when we have determiners, we could know whether the thing we are talking about is definite or indefinite, for example, whether it's plural or singular with that and those, things like that. Conjunctions will help us put things together, so make more complex structures from simpler ones, but they are actually not adding much meaning, so they don't have much meaning by themselves. Yeah. So the task that we will be working with, so in general, as I mentioned before, we are interested in sequence labeling. So we're interested in assigning a sequence of labels to a sequence of input, or an input sequence. In part of speech tagging, the task is to automatically assign a part of speech or part of speech tags to a word sequence. So we're given a word sequence, and we want to assign a part of speech per word. So 10 words, then 10 parts of speech. This is not very easy. It's a non-trivial task because words are ambiguous, as we have seen before. So a word like a fly could be a verb, it could be a noun. So we depend on the context to, again, know which part of speech we should assign. The task itself, part of speech tagging, is useful for several applications. So one thing is we can use it for pre-processing, for parsing. So the thing that we will look at in the following lectures. So assigning syntactic trees to sentences. But it's also directly applicable to things like text-to-speech systems, things that sort of read out. So a system that reads out a text sort of makes speech. So, and why is that important? Because we have some words like this one here, which have the same orthography. It's written exactly the same, but when it's a noun, it's pronounced differently from when it's an adjective. So we say content and we say content, right? So content mean so the content of this lecture. So I hope you are content with the content of this lecture, right? So this stress pattern is defined based on the part of speech of the word. So if your phone is talking to you, if your Siri is saying, I hope you are content with the content I am providing you, then you won't be content, right? Because it's not putting the stress correctly. So this is a direct application of why we use part of speech tags. The difficulty and the usefulness of the problem is dependent on the tag set. So you saw these distinctions that we made. A noun could be a proper noun, etc., singular, countable, uncountable. So the more fine-grained, the more difficult would be the task. And the more coarse-grained is possibly the easier, but maybe the less useful. So In general, when we work with part-of-speech tagging, we will assume a set of part-of-speech. And in our case, we are going to assume the one introduced by the Pantry Bank, which is what you are using for the assignment already, I guess. It defines 45 tags. So this is our inventory of tags. And these kind of tags include things like NN is a noun, NNS is a noun in the plural form, NNP is a proper noun, JJ is an adjective, JJR is comparative form, JJS is the superlative form, and so on and so forth. So this is just someone has sat down and decided that we need this data set. It was motivated basically on mostly on things that can be observed from English orthography. So things like a proper noun, you could easily observe that. You could easily see it from the capitalization, because that's how proper nouns are written in English. But again, that's not very central to us. What we care about here is that we have 45 tags and we want to assign them to sentences, sequences of words. There's a similar thing for Norwegian, but I'm not sure I actually completely understand it. But I kept it here, so in case you want to look it up later on. So there's also a tag set for Norwegian. Okay, so again, so this is what we are interested in, flies like the wind. Before we talked about flies like an arrow, and there our interpretation was a little bit clear to us. Here, one can argue that flies can actually, the insects can like the wind for some reason. Makes them faster, or I don't know why. So again, we have this problem here. Is flies a noun, the plural form, or is it a verb in the third singular, what was it again, form, which is like he likes, right? I say I like, he likes, he flies, it flies. And what about also like? Is it a verb or is it a preposition? So this is what we want to find the most likely sequence of tags given this sentence. But a normal text, so when we look at English text, all we see is words. We don't see tags. So we consider the part of speech tags to be an underlying skeleton, a hidden part of the sentence that influences our interpretation of the sentence. It influences the sentence shape. So we will have this, from now on, we will talk about this hidden part of the sentence, which will lead us to defining a structure that consists of an observable, seen if you want, sequence, which is the words, and unseen, hidden sequence, which is the part of speech tags. And when we have such a structure, hidden Markov model are the perfect models to actually model this these two sequences of seen or observable, what we call them observation sequence, which is in our example here the words, and the hidden state sequence, which is the part of speech tags. So if we go back to this generative story that we introduced last time, but now use it with hidden Markov models. So we have, this is the start of the sentence symbol. It's a pseudo state from now on, we'll call it. And we are asking what's the most likely part of speech to start an English sentence. And then let's assume it's a determiner. So this is like what we have done before. So this is, you can think of this as an n-gram model that is working with part of speech instead of words. But here comes the part that differentiates our hidden Markov model to the n-grams, which is these observations. This is an observation, and we say, assuming that the determiner was dt, was generated for us, and it was dt, what's the probability of seeing this observation the given the determiner dt? So this part and these two things together will be, as you will see later on in a few minutes, is the building blocks on how to work with hidden Markov models. And then we continue. So we say, given a dt, what's the most likely part of speech tag that follows the dt, and so on and so forth. And again, yeah. So this is a start pseudo state, and that's the end pseudo state, and these will be. We will focus more on these also in this lecture more than we did last time. So let's try to formalize that a little bit. So what we would just show is this is a bigram, right? So this is a bigram because we're only looking at the immediately preceding state. So for a bigram, hidden Markov model, and an observation sequence of length n. So we have a hidden Markov model, and we have an observation sequence of length n. Sorry. We want to compute the joint probability between S, which is the hidden sequence or state sequence, and the observation sequence. And this turns out to be, again, an application of the chain rule. So what we are computing here is for each state or for each time point from I equals 1 to n plus 1, we compute the probability of state I given state I minus 1, which is the horizontal errors we saw in the previous slide, and the probability of the observation OI given the current state SI. And this we take the product of all of these, of course. So this is a product sign for I from 1 to n plus 1. So when we say I equals 1, this means that for S1 we are conditioning on S0, which is the start symbol. And since our I goes up to n plus 1, it means that we also include the end pseudostate or end symbol. So this part, this term here, we will refer to as the transition probability. Because it models the probability of transitioning from one state to another. That's why we call it transition probability. And this term here we will refer to as the emission probability, because it models the probability that a given state, generates or emits this a particular observation. And so the computation of in hidden Markov model will basically be a multiplication of the transition probabilities with the emission probabilities. So again, transition probabilities is we're transitioning from one state to another. And emission probability is that the probability of a state emitting an observation, which is basically the probability of an observation given a state. So this is how we would define a Markov model, but how can we actually use it? So what are the specific problems that we can use it for, or problems in terms of probabilities here? So what we just described basically is one application, which is the probability of a sequence and an observation. So a probability, we can compute that through the hidden Markov model. But this is really a rare or uncommon problem in natural language. So it's uncommon that you actually know the hidden sequence of or state sequence and the observation itself, and you want to compute their joint probability. You can also compute things like the probability of the observation sequence. Big O is always sequence in this slide. Big O and big S are always referring to sequences. So the probability of the sequence of observations O given O, or knowing O, given not in the conditional sense here. So what would this be? What is this? Does it ring a bell, or does it? Do you feel that you have seen this, computing this probability before? It's something we have done, but described here in different terms. So if our observations are words, so and we say we are computing the probability of a sequence of observations, so then we are computing the probability of a sequence of words. So this is basically language modeling. So our observations are words in this case. So we're doing language modeling through HMMs because we can do that. It's not only limited to n-grams. So we can compute the probability of an observation sequence using HMMs, but this will actually require more. It will be more expensive in terms of preparing the training data, because in n-grams we were only looking at text, so just corpus of text, and in this case we will be looking at parts of speech and the text. So we require the data set to have been annotated with parts of speech. Yeah. The hidden sequence, if you think of the difference between the hidden sequence and the observation sequence. So if you think of the words in the text, this is something you observe. But there is an underlying property of these words. These are the hidden states. So this is something that we want to predict. So it's there, we know it's there, and there is a relation between the words and this sequence of or state sequence, but it's hidden. We don't know it, and that's why we want to predict it. And that's what we will try to do here next, which is basically we use HMMs to find the sequence S that maximizes the probability of S given B. So this is basically part of speech tagging. So we're given an observation sequence O, and we are looking for the sequence of parts of speech that maximizes this term here, which is the probability of S given O. So that's the task we will be working with now. But so these are things that we can do. But before we can do these things, how can we actually, so before we can do these things, we will actually need to learn the parameters of HMMs. So, and when I say parameters, I'm referring to transition probabilities and emission probabilities. How do we learn these? That's something we will look at. But this is something that we need to do before we start working with it. It's similar to what we have done in n-grams. So we learn the parameters, and we then can apply these or look for solutions for these problems. So as I said, our observations will be words. So sometimes we'll be using WI instead of O. So big W would be a sequence of words, and this corresponds to our observations, to the O. And our states would be the parts of speech, and then we will be using T. And so how do we learn the parameters? How do we learn these transition and emission probabilities? We basically also assume a supervised machine learning technique here. So we assume the existence of a data set, training data set, that has annotated all the words with their part of speech. And we use that to learn the transition probabilities using, again, maximum likelihood estimations. So the probability of a tag I, given the immediately preceding tag ti minus 1, would be the count of this, what we call tag biogram, normalized by the count of the conditioning tag here, which is, so basically we count how many times we see ti minus 1 followed by ti, and then we normalize that by how many times we see ti minus 1, regardless of what happens afterwards. So this is exactly the same as we have done in n-grams, but here we're working with tags. There we were working with words. So this is the exact same equation. And we can do the same again with the emission probabilities, but this time we compute the pairing. So how many times a word I occurred with the tag I. So the probability of WI given TI, so would be how many times the pair, this word tagged and this tag TI, how many times they occurred over how many times, or normalized by how many times the tag ti occurs in our corpus. So again, it's a straightforward application of the maximum likelihood estimations. This is, yeah, so we have computed the probabilities and using the maximum likelihood estimation, and then we multiply them, and this is something I mentioned before in the last lecture, but it also applies here, is that probabilities will be small. They're definitely between 0 and 1. So the more you multiply, the smaller the probability and the probabilities, and the more you multiply them, the more likely you will end up having an underflow and your floating point underflow. So we solve this problem by working in moving from the linear space to the logarithmic space, where we can add instead of multiply, etc., etc. Again, also the same problems that we had in Ingram models will apply here, meaning that there will be data sparsity, so there will be tags we haven't, or bigrams of tags that we haven't seen. So we need to apply smoothing and again move some of the probability mass from very frequent events to infrequent ones. Is this clear so far? Yeah. So we are going to work with parts of speech tags, as I mentioned, but to sort of give an example of how we can use HMMs, we will use a much more simplified example in this case, and just to make the problem tractable and to be able to draw the transition graph, as you will see in a few minutes. So you have a problem here that, so you are in the year 2800, for example, and you are studying the history of global warming. So humanity survived until then, and you were assigned this task of studying the history of global warming. But you had a problem, which is in the summer of 2007, the records of the weather in Baltimore were lost. So we don't have any track of the weather at the time. But luckily, a person called Jason Eisner, who likes to eat ice cream, kept in his diary the number of ice creams that he ate every day during the summer of 2007. So even though Jason likes to eat ice cream, but we know that there is actually a relation between hot days and number of ice creams. So in hot days, there will be the number of ice creams will be influenced, meaning that it will be more, and in cold days, the number of ice creams will be less. And also we know that the weather does not change randomly. So it's not cold, hot, cold, hot, cold, hot. You can actually predict the weather based on of today, or of tomorrow based on today, or today based on yesterday, etc. So this setup fits for a sequence labeling situation, and what we are interested in is to recover the weather measurement in this time, which is the summer 2007. So we have a sequences of observable data, which is the number of ice creams Jason ate, and we want to predict the hidden sequences, the hidden state sequences, which are the whether the day was hot or cold. So again, this is, if we formulate this as a hidden Markov model, this problem, we define our hidden states, the things that we want to predict, or sequences of states that we want to predict, as hot and cold. So this is how much we are interested in temperature. It's either hot or cold. And we will have then two states plus two pseudo states, so beginning of the sequence and end of sequence. And the observations will be drawn from 1 to 3. So what this means is that Jason ate at most 3 ice creams, so he didn't eat more than three ice creams in one day. And there was no day where he ate nothing, so that's why we don't have 0. So it's 1, 2, 3. So this is our space of possible, or where the observation will be drawn from. So we will have things like 1, 1, 1, 1, 2, 3, 313, etc. So we can draw, so this is a simple problem. We can draw it in a transition graph, so to represent our transition and emission probabilities. So the circles you see here, these are representing the states, our states. So we have one cold, one hot, and we have two pseudo-states. The arrows going from one state to the other or into the state itself are the transition probabilities. So what's the probability of going from, or what's the probability of cold given start symbol? That would be here. And for the two non-pseudo states, the cold and hot, we have a table of emission probabilities. So meaning that for the day when, or for the state when or the hot day state, we have probabilities like what's the probability of Jason eating one ice cream given that it's hot, and what's the probability of Jason eating two ice creams given that it's hot. So these are values that we just hypothesize, or we just now put forward to use in our computation. And what we are interested in, again, is to produce a sequence of states, hot, cold, hot, cold, hot, hot, etc., that maximizes this term here, the probability of the sequence given the observation. So we look at the observations that Jason wrote, how many ice creams per day, and we want to predict or to find the sequence of states S that maximizes this conditional probability here. So if we revisit our definition of hidden Markov model and how to compute the joint probability of a sequence given, a joint probability of a sequence and an observation, a state sequence and an observation sequence. That would be the product from I1 to n plus 1 of the transition and emission probabilities. So for each time point, we compute the transition probability and the emission probability at that time point, and then we multiply them all together. But that computes the joint probability. We are interested in the conditional probability here. We're interested in the probability of S given O. We know that we can write this term here as the joint probability of S and O normalized by the probability of O. So this is per the definition of conditional probability. So then our problem can be rewritten as follows. We want to find the state sequence S that maximizes the probability of S given O, which means we want to maximize this this fraction here, or this formula here. And argmax is, do you know have you seen argmax before? Or is it? Yeah, so not so many. Okay, so argmax is basically an operation that searches for the S that maximizes this this term here. So basically you can think of argmax as a search problem. The search problem will generate all possible S and then plug them into this equation and pick the one that returns the highest probability or the highest value of this term. So you could have argmax, argmin, etc. Argmax, and then it's defined on a variable, and that variable is S. So this S we are changing and changing until we find the one that maximizes this this term here. And so in this equation here, there is one constant actually. So we are searching for the S value that maximizes the term here, but there's the probability of the observation is always the same. So the observation is not changing. So while we are searching for the S that maximizes this, we are always dividing by the same number, which means we can simply just drop this number and keep on and get exactly the same value, because this is not changing. So what happened here is we actually we represented our problem, which is looking for the S that maximizes the probability of S given O in terms of the joint probability. So that's what we have done here. And this, the joint probability, we know how to compute. It's over there. So now we have sort of what we need to compute this, to look for the sequence of hot or cold days given the observations that Jason has written. So our problem again, in plain English, what is the most likely state sequence S given an observation sequence O and an HMM? So an HMM is defined by its parameters. So we have here the parameters. These are the transition and emission probabilities from the example we've shown before, this transition graph. So and we are asking if the observation in Jason's diary is 313. So he has, the summer was very short, so that's only 3 days. First day 3, second day 1, and the third day 3. What is the most what's the state sequence S that maximizes the probability of S given O? How can we find that? So we can basically enumerate. So we enumerate all possible sequences of states and then compute their probability given the equation we just shown in the previous slide. So how many sequences do we have? So we have 3 days. We have 2 possible states per day per observation, if we speak in the HMM language. So how many sequences do we have then? Yeah, 6, and it's 2 by 2 by 2, so it's 2 to the power of 3, or 2 to the third, right? So we do that then for, no, did you say 6? Sorry, it's 8. Yeah, I didn't. Yeah, it's 8 because it's for each observation you have 2 possibilities, and then that would be 2 by 2 for the second choice and 2 for the third choice, and this is 8. So we compute the probability of 8 sequences, and we pick the one that has the highest probability. Simple. But there is tricky part here, and I will leave you to think about it. Think, how is it really that simple? Are we being deceived here? Think about that in the break if you want, and we'll come in 15 minutes. Let's start again. So before the break, we introduced the problem of, actually I forgot to mention that this is called decoding, when we look for the best sequence of states that give us the, or as written here, so the most likely state sequence S given the observation O and an HMM. This is what we refer to as decoding. So before the break we said that we can actually find this sequence S by enumerating all possible sequences and then computing the joint probability of each of these sequences with the observation O we have. But what's the problem with this approach? Do you see? Yeah. Yeah, exactly. Yeah, it has exponential complexities. You know, here we have a toy example that's far from the reality. So the number of sequences is 2 to the third. So this would have, so this approach would work when we have something like this. So we have only 2 states and we have a very short observation sequence. It's workable, it's doable, and we can enumerate them all and do all the computations. But it's actually, so the growth of this algorithm is exponential to the length of the input or sort of the observation sequence. So L is the number of states, N is the length of the observation and observation sequence, and the algorithm will grow with L to the N complexity, which is pretty difficult to compute with when we want to enumerate all of the sequences. Another observation that we should take into consideration is that while we were computing the probabilities of these sequences, the state sequences, there were some overlaps or some common prefixes. So we computed the probabilities for some of these prefixes over and over. So for each sequence, we would compute the transition and emission probabilities, even though there are actually, like this, for example, here, common prefixes. So knowing this and knowing that our problem is very expensive to solve, dynamic programming can be a solution. So dynamic programming can help us subdivide or decompose a complex problem into sub-problems. And while we are decomposing this problem into sub-problems, we also can record the solutions for these sub-problems and reuse them again. So we can compute the probabilities for the prefixes, the common shared prefixes, and then reuse that. So we can clearly apply dynamic programming here to solve the problem of finding the sequence S that maximizes the probability P of S given O. So you've probably seen, and of course, I mean the problem that we want to solve with dynamic programming we should be able to express it recursively, in a sense. You probably have seen examples of dynamic programming's algorithms. So shortest path, minimum edit distance, and longest common subsequence, etc. We are interested in Viterbi algorithm. This is the dynamic programming algorithm that we will use to decode and the decoding phase in HMM, and looking for the most likely or most probable sequence that would, or meaning, in other words, we were looking for the sequence that maximizes the probability of S given B, given O. So again, our problem is to maximize this. Here we have written out the sequence. So instead of big S and big O, we have the sequence, states from S1 to Sn and O1 to On, and we want to maximize the sequence of states S1 to Sn given, we want to find the sequence that maximizes S given O, sequence of states given the sequence of observations. And again, that's basically a multiplication of the transition and emission probabilities at each time point. So, and another thing I forgot maybe to mention is when I say time point I mean an element within the observation and the observation sequence and the state sequence. So basically just an index, but we refer to it as a time point I. So element I within the sequence, basically. So this is our problem, and we want to define it recursively, in a sense. We want to define these sub-problems that will help us formulate the decoding in a dynamic programming manner. So we introduce a variable vi of x, and the meaning of this variable, we define the variable as the maximum probability of that the ith state is x, given that we have seen the observation sequence up to the ith point. Again, so it's It's vi of x is the maximum probability. The maximum is important here, so it's the maximum probability of state x at time point I, given that we have seen the observation sequence up to I. And this could be defined, this vix, or could be computed by, so we look for the max over all possible states from, so k1, k from 1 to L. So if we denote the states in numbers, and we say the first state is 1 and the last state is L, so the size of our states, we can compute vi of x using this equation. And what this equation has, first, this is where we see the recursiveness, so, or the recursion. We want to by defining this as a recursive problem, we say that we can look up the vi minus 1 of k, meaning we can find the maximum probability of k, of the state k, at time point I minus 1, given that we have seen the observation sequence to up to I minus 1. So this we have computed already, because this is how we will define the recursion. So we look up the maximum probability for all, so we do this for all states, the maximum probability of being at this state and time point I minus 1 times the transition probability from the state k to x, which is given the probability of x given k, times the emission probability, which is the probability of the observation I given the current state x that we're looking at here. So I'll repeat it again, but you will get a chance to see it in practice in an example. So what we are saying here, we are claiming, is that we can find the probability, or the maximum probability of some path up to point I, or some path at the state x up to point I, by assuming that we have computed the maximum probability of all possible preceding states, which is saved in vi minus 1 k, and k will loop through all the possible states, and we multiply that by the transition probability for the state k, from the state k to x, and the emission probability of the observation at the current time point, which is I, given the state that we are computing, or whose probability we are computing, maximum probability. Then, so for all of preceding states, for all possible ways of moving from the preceding state to the one that we are interested in, we do this computation and we pick the one that has the max value. So we'll look at this. I maybe just remember for now that there are 3 terms when we are going to fill in the VI values. There will be 3 terms. We will be depending on the value of VI minus 1 for some state k, and the transition probability and the emission probability. What this will give us, so when we arrive at the final state, the end state, the pseudo state actually, this will give us a number, will give us the probability of a sequence S for some sequence S that happens to maximize the probability of S given O. But our problem again is to actually find the sequence itself. So we want to find the sequence, not only the probability of the sequence that maximizes the term we defined. So in order to do so, in order to be able to backtrack or go or trace the path that we take, we want to keep back pointers, so-called back pointers. Again, this will be clear now in the example. So, but we will need something to keep track of how we moved through the graph that you will see now. So let's say that this is our problem again. We have the observation from Jason's diary 3 days, observation 1, 2, 3. So that's our O observation sequence, has a length of 3. We draw a matrix here in which we have for each observation the possible states that we have. So CH for each of them. And we have the pseudo states. So start state and end state. And we want to fill in this matrix with probabilities. So we want to compute the probability. So if we start from here, we want to compute the variable that we talked about before, which is V. So here it would be V1H, which is the maximum probability of the state H in time point 1, given that we have seen the observation up to here so far. So we have seen 3. Now this is an exception or a trivial way or case to compute, because there's only one way you can actually start, which is basically just from the start state to hot. So this is only one path. So we're going to go through different paths here, but this here we only have one, which means we don't need to maximize in a sense. So this is our max. This will be the multiplication of the transition probability and the emission probability is our max, which means this will be our V1H value. So we multiply the probability of H given S, meaning the probability of moving from the start symbol to, or transitioning from the start symbol to the state H, and the emission probability, which is the probability of 3 Jason eating 3 ice creams, given that we are in state H. We have the values for these, so we simply multiply them and record that in our matrix. This is our matrix here and has V1H here. And we want to keep, this is the back pointer we want to keep, so we know where we come from when we look at this value. So how did we get this value? Here it's trivial, there is only one way, so it could only come from S. So, but still, these red dotted lines are going to be our back pointers. We do the same for the state C here, again at time point 1. So V1C, it means the maximum probability of being at state C at time point 1, given that we have seen given the observation sequence up to 1. But things will get more interesting when we, again, we have the back pointer. It will be more interesting when we move to the next state. So here, we are at state H in time point 2 now, so O2. And there are two ways that we could actually arrive at this state. So we could transition or move from a hot state to a hot state, or from a cold state to a hot state. So there are two possibilities now. And we want to find the maximum probability of this, of state of H in time point 2, based on all possible preceding states. Meaning that we want to compute for the first one here, transitioning from H to H, we compute the probability, the transition probability, H given H, and the emission probability 1 here given H. And we multiply that by the maximum probability of having been in H. So these are the three terms that I asked you to remember. So first one would be the maximum probability of, so what we refer to as Vi minus 1 of K. So the maximum probability of being in state K at time point I minus 1. So that's, in our example here, would be V1H. So this we multiply by the transition probability and the emission probability also. And it's written here in a sort of more shorthand manner. So we already multiplied these two and we got 0.12, right? So basically it's the three numbers here. So it's 0.32 times 0.6 times 0.2. And we do the same here. we're looking for the max. We're looking for the path that gives us the maximum probability. So we will have to consider all preceding states that could lead us to the current state we are interested in. So we do the same here, meaning that we also look up the vi minus 1 at C this time, at state C. We have it, we have computed this, and we multiply it with transition and emission probability, and we compare the results. So we compare, and we'll find that coming from H has a higher, or gives us a higher probability, and we're interested in the maximum probability, so we will keep the back pointer here. So we will say that the maximum probability of being at state H time point 2 is 0.0384, and that comes from transitioning from H to H. Is this clear? So we continue, we do the same as well here, and so on. So again, we find also that this maximum probability is comes through moving through from H to C. We do the same again until we arrive at we reach the pseudo final or end state. So there we have, this is the probability, or the probability that of the sequence, and as we mentioned, we are interested in the sequence itself, not the probability only. So we want to backtrace. So here not backtrack, I guess. It's just go back in the path we followed to arrive at this number. So here it's clear that we got this number by moving from H to end state, not from cold. So we keep that, and we output H. And then when we are here, to get this maximum probability, we had to move from H to H as well. And again, back to this state, we know the path that led us to this maximum probability, so we also output H, and that would be our hidden sequence. That corresponds to the observation we have. So this sequence will maximize the probability of S given O. Is it clear? Do you get it now better with the example? Okay, good. So this is the pseudocode of the Viterbi algorithm. So in the assignment, you are actually asked to implement the algorithm and train a tagger and also evaluate it. So I won't go into the details, but two main components here. We want to have a matrix. I'm saying matrix just conceptually. That doesn't mean you need to use a matrix in the assignment itself. So we need a matrix to store the V values. So we call this the Viterbi matrix, which has dimensions, 2 dimensions, n and L plus 2. So n is the length of the observation sequence, and L plus 2 is the size of the tag set L, plus 2 for the start and end state. And we also have the same for a back pointer matrix that keeps track of the path we take to find the maximum probability at each state. We have a for loop to initialize. So that's the trivial part that we have done in the first step, which is basically a multiplication of the transition and emission, because we don't have other ways to come to the first state, the first column. And then we have this nested loop where we compute the Viterbi, and this is, as you can see, an immediate translation of the formula we provided before. So it's V for all. So this is the yeah. I'm not going to explain this again. It's basically for all possible states or preceding states. We look at the maximum probability for that state at a given time point I minus 1, and multiply that by transition probability from that state to the current one, and the emission probability between or the emission probability of observation OI S. These are not joint probabilities, of course. I mean, this is pseudocode, so this is yeah, and so on and so forth. So a bit of divergent here. So the big O notation, it's a way to describe complexities of or the complexity of an algorithm. So most of you maybe are familiar with this. And it measures or it describes the worst case scenario of the order of growth of the an algorithm in terms of the size of the input. So in our case is the observation sequence. That's the input. That's the things we see and not we predict. And normally when we have different terms that are dependent on the same variable, we are only interested in the largest one, the largest order of them. So L and L, quadratic L, then we're interested in quadratic L. And constant factors are usually ignored when we compute the big O notation. So we're looking for the worst, really the upper bound of the running time for this algorithm. And you can more or less determine this by looking at the loops in the pseudocode. So if we look again here and try to determine the complexity of the Viterbi algorithm. So we have an initialization loop here, which runs sort of from 1 to L. L is the size of our tag set, right, or states. Then we have a loop here from 2 to n, so that's growing by the size of n, and n is the length of our observation sequence, our input, the sequence of words. And we also have another for loop running from 1 to L, and yet another one. But where is that? No. There is something here that calls for a loop within these two lines. And that loop runs L times, in a sense. Can you see it? Sorry? It's the argmax, yes. It's so, as we said, the argmax is a search. So it's not the max, this one, this is a comparison. It's the argmax. The argmax is a search problem, or a search operator, if you want. So it will look for the S that maximizes this. So this is there. Then there is a loop actually from 1 to L. So it's not described. It's not written as such in the pseudocode, since it's not written as a loop, but this is still a loop. So we have then the complexity here. So we have two there are actually 3. So we have L to the power of 2 and n. So quadratic L n n multiplied by n. And then we have finally also one for the back pointer. So when we trace back the path, we have one loop n here. So in big O notation, this would have a complexity of L to the power of 2 and multiplied by n. So it grows quadratically by the number of or the number of tags in our tag set. So the 45 tags in our Ben-tree bank tag set, and linearly in terms of the input sequence or observations. Do you think this is a good or bad sort of complexity? Any feelings? Yeah. But what's the thing that we can sort of, in a sense, we are guaranteed to have fixed and what's the thing that will be arbitrary. We don't know how long it is. The n, exactly. So growing linearly and in terms of n is not is good for us because we don't know how long the input sequence is going to be. But L we know. I mean, we have 45 tags, and that's not going to change. 45 states. So at least we could actually sort of have a sense of how long it will take. But so if it were the other way around, then n could be extremely large, and then this would be slower in a sense. Okay, so that was how we compute we find S, the state sequence that maximizes the probability of S given O. So another task that we might want to do with HMMs is what we also explained before, is the probability of an observation sequence O, and what we refer to as language modeling. So we want to do language modeling using HMMs, the probability of an observation. So given an observation sequence O, we want to determine the likelihood PO, the probability PO, according to some HMM. Now this is going to be, we can't get this in a sort of straightforward manner from the HMM, because we know how to compute the joint probability, and we need to somehow express this probability of O through the joint probability. So let's say generally and very broadly speaking, if you have many ways or many events that could lead to the same outcome, you can compute the probability of this outcome by summing the joint probability of these events with the outcome itself, right? So here what we are saying is that in order to compute the probability of an observation, we will sum over S being the sequence of states or hidden states. We will sum the joint probabilities of all possible S with O. So in other words, we will sum the probability of all the joint probability of all the possible sequences we can generate in our model together with the observation, and this will give us the probability of O. So if we make this concrete, so say that we want to compute the probability of this observation sequence, again in the ice cream example. So probability of 313. What we can do then is sum the probability, the joint probabilities of 313 with all possible state sequences. So with all possible state sequences, that's 8. So we do that, compute joint probability, and then this time sum them. That's what we do to get this probability. But again, I mean, as you can easily see, this would have the same problem as before. If we have a large n and a large L, this is an exponential growth, so we can't actually do this. We can't just enumerate them all and sum. We need to apply, again, dynamic programming. So luckily, it's this algorithm is quite parallel to the Viterbi algorithm, so as we will see. And another thing, actually, just before we started this, I wanted to mention is why it's important to actually read the book, because the book starts by introducing the forward algorithm and builds on that to explain the Viterbi. What we are doing here is we are going the other way around. So we're trying to give you different ways to see the problem so that you can actually understand it. So you might find the way in the book more intuitive, maybe. So it's important to read that as well, not just listen or come to the lecture. So we will use dynamic programming to estimate the probability of an observation O using some hidden Markov model. Again, with dynamic programming, what we can achieve is to store and reuse results of partial computations. And we will introduce a so-called trellis, which is basically also a matrix. So there we use the matrix, this Viterbi matrix with V. Here we will call it alpha. So in Viterbi we used this V, and we defined Vi of x, I'm thinking Viterbi now, to be the maximum probability of the state x at time point I. Now we would change the definition a little bit. So we will say each cell in this trellis, which is alpha I x, will store the probability of being in the state Sx after seeing the first I observations. So the meaning of alpha Ix is the probability of x at time point I, given that we have seen observations up to I. So if you contrast that to Viterbi, there we were saying maximum probability of state x at time point I. Here we're saying the probability, no matter which path actually we want to take all the paths possible that will lead us to this state and sum them together. So that's what we're doing here. So for all states, K1L, for all preceding states, we look up the value alpha I minus 1 of state K, multiply that by the transition probability of x given K, and the emission probability of the observation I given the current state, again K, x, sorry. So we're basically using the sigma here, the sum, instead of the max. Is this clear? Do you see the difference? We will go through again through another example, or basically the same example, but this time we are looking at computing the probability of the observation. We're not interested in finding the sequence that maximizes P of S given O. We're just interested in the probability of O, which means also that we don't need back pointers. So we're not producing anything. We just want a P of this, a probability of this observation. So we write out our observation sequence, again 3 elements over 3 days, and we have our matrix. For each day, for each observation, we have the possible states on this in this observation, or on this day, sorry. So we, again, this would be the trivial case. So there's only one path from the start state to a hot day. So that basically boils down to multiplying the transition probability by the emission probability. The same here. So, and we are recording alpha. So alpha 1h means the probability of having state h at time point 1. Now we move to the more interesting part again. So we have we are at time point 2. We want to compute the probability of state h at time point 2. And that could be computed through summing the probability of moving through this path and this path. So that's what we are doing here. So again, we just really parallel to what we have done in the Viterbi algorithm. We look up the probability of being at state h at time I minus 1. So here we have that, it's 0.32, and we multiply that by the transition probability of hot to hot, so hot given hot, and the emission probability, and we sum that with the probability of, again, we sum that with the multiplication of alpha 1c with the transition and emission probabilities here. So here we're not picking, we're just summing. That would give us the probability of being at this state so far. And again, so on and so forth. We do the same, and we arrive at the final state or end pseudo state, and we have the probability of this observation sequence. this is this clear? You have any? Do you see the sort of the parallelism between the two algorithms? So it's basically summing instead of looking for a maximum value. That's again we have the same parallel structure in a sense, more or less, but without back pointers, and we in the pseudocode, and without the sort of, we replace the argmax with the summing over the probabilities so far. And finally, to evaluate a tagger, this is something you already know, but just probably a reminder. It's like evaluating any classification system. So we have a training data set, we have a test data set, we train on the trained data set or training data set, and we test on this completely separate held out test data set. So in order to evaluate our tagger, the measure or the evaluation measure is normally accuracy, which is basically the number of correct tags normalized or divided by the number of words, or sort of, and so the number of words corresponds to the number of tags our tagger predicted, right? Because we want to predict one tag per word. So basically this is the same. So the number of correct predictions over all the number of predictions we made. So it's like any accuracy or classification system that is for which we are computing accuracy. Sometimes people use something called error rate, which is basically how many times we, or sort of the rate of making errors, which is basically 1 minus the accuracy. So not very that doesn't tell you much different information than what you actually know in accuracy, but some people use it because it looks better to say that I have reduced the error rate by this much, and then you report it, and it would be like, I don't know, 50%, but what you have actually maybe you have reduced a very small portion. Anyway, you have an evaluation script for, so we are in the assignment, you have an evaluation script that will actually count the accuracy for your tagger. And so a quick summary. So we looked at part of speech tagging as a sequence labeling problem. So a sequence labeling problem, we are given an input sequence, and we want to produce or predict a sequence of labels. We used hidden Markov models to model this construction or this structure that we have of observation and hidden sequences. So the observation would be the words that are observable in the text, and the hidden states or the hidden sequences are the tags. And to learn the parameters of an HMM, a hidden Markov model, and when we say parameters, we mean the transition and emission probabilities, we use maximum likelihood estimation, and we assume the existence of a training corpus where words were annotated with their part of speech. Otherwise, we can't compute anything. We use the Viterbi algorithm for decoding, meaning when we are interested in finding the sequence, the hidden sequence, state sequence S, that maximizes this probability here, which is the probability of a hidden state sequence given the observation sequence or the observed sequence. And we use the forward algorithm for computing the likelihood, meaning that if we want to use an HMM as a language model, we would then be using the forward algorithm for computing the likelihood of an observation. I think that was all. Yes, so do you have any questions on this? Or things that you don't grasp or fully grasp? Otherwise, I will go quickly to the example that I confused you with last time. So